Hey, what's up, guys? This is Sheng here. So this time, LeetCode number 1168, optimize water distribution in the village. Okay, so this time we have n houses in the village, and we want to supply water for all the houses by building wells and laying pipes. Okay, so basically we have n houses, and we want to supply waters to all of them. And for each house, right, we have two options. We can either build a well inside it directly with the cost of this well. Okay, note that the -1 due to zero indexing because this house is labeled from 1 to n, right? Not from 0 to n minus 1. Or the second option is that we can pipe in water from another well to it. Okay, and the cost to lay pipes between the houses are given by the rate pipes, right? So where we have a house 1, house 2, and the cost between those two. Okay. And yeah, and then we just need to return the minimum total cost to supply water to all houses. Right. So that's why, for example, we have this we have 3 houses, right? And we have these wells. So wells means that, to build a well for house 1 is the cost is 1, right? And then 2 and 3. And the pipes means that, between 1 and 2 we have to build a pipe, the cost is 1. And between 2 and 3 we have a cost to build a pipe also as 1. That's why we have 3 here, right? So the strategy is that we build a well. We build a well in the first house, and then we use 2 pipes to connect them. Okay. So then we have some constraints, right? So obviously this one is like it's a graph problem, right? And this one since we're getting the minimum total cost, right? So this one is exactly what is a minimum spinning tree, right? So I think most of you should know this minimum spinning tree, which means that we have a bunch of edges, right? We have a bunch of edges in the forest, basically, right? Doesn't really matter how many edges we have, but we have bunch of edges, and each of the edge has its own weight, right? And we want to connect. Basically, we want to connect odd nodes with minimum cost together, right? And that's exactly what this problem is asking us to do, right? And so the way we're doing this, so connecting all the nodes, is by using the crosscar algorithm, right? Which means that we'll be using a union find after sorting the edges by its weight, right? So what that crosscar algorithm does is that basically we have edges with a weight, right? And we sort the edges from with the edge with the weight from the smallest to the biggest, and then we'll try to do a union with each of the edge, right? So with each of the edge we have u and a v, right? So we only union when those two are not connected. Okay, and then that's when the unit is success, then we'll accumulate that cost, right? And by the time all the nodes they're all union together, and then the final cost will be our answer, right? So basically we'll be using the crosscar algorithm plus union find to solve this problem. But there's another thing we need to consider here, is that we have 2 options to connect the house. We can either use an edge, right? Or we can simply build a well inside the house directly. So what does that mean? Let's say we have 3 houses, right? And let's say between each of the house we have a pipe, okay? And each pipe has a cost of 100, right? But let's say the cost to build a wells in each of the house it's just 10, right? 10 itself. Then obviously the minimum cost to supply water to all houses is what? Is 30. which means we'll not use any of the edge, but instead we'll build a well for each of the house directly, right? So if that's the case, then seems like we cannot, there's like an issue here because we have some unaccounted factor here other than the edges. Then how can we utilize this crosscut, right? And with the edges. So the solution is that we have to think it out of the box, outside of the box, which means that we have to convert it into a regular crosscut problem, right? Which means that, if you think about this, right, how can we convert this like separate wells, right, to an edge? So that's the problem we want to solve, right? So the way we're converting is that, let's say we have another node here, right? So this is another node n here, and if we build an edge, right? So this node n represents the well, a common well, okay? If we build an edge to this well to each of the nodes, okay, with the weight of these wells, right? Then we're basically converting this the single value into an edge, right? By introducing a dummy well node here, right? I mean, if we do that, we have we have 3 more edges with a weight of 10, right? After applying the crosscut algorithm, obviously we'll have 30, because after union these 3 edges, all the nodes have already been united together, together. And so that's it. So that's the only thing we need to do here, by introducing more dummy edges to this graph. Okay, so I think that's everything, and let's start coding then. So since we're going to use the union find, right? So let's implement the union find template first. I have already implemented this union find many times, so I just go ahead and type it in here, type it down here. So we have a union, we have find if x does not equal to the parent of x, right? Then we have parent of x equals to the find of parent, right? And then we return the parent of x. So this is the find with a path compression, right? And then we have a union, right? Union is going to be x and y, right? And then the R1 equals to find root 1 equals find x, and the root 2 equals to the find of y. Okay. If R1 does not equal to R2, right, we set the parents of R2 to R1 again, right? So here I skip that, the weight. Basically I skip that ranking comparison here. So if you really want to make both if you really want to make the union O1 time complexity, besides the parents, we should also introducing a ranking array here. So basically, every time we always assign the component with a lower ranking to the component with higher ranking. That's why we try to make this a union or make this tree balanced, right? But here I've simply just simplified it, right? Okay. So that's that. Basically, that's the union find. Pretty straightforward, right? Simplified version of union find. And then we have edges, right? So let's do the edges here. So for edges, let's add edges from the pipes first. So we have a U, a V, and the cost in pipes, right? Edges dot append. So since we're going to sort by it, so first one is gonna be cost. Second one is going to be a u minus 1, a v minus 1, right? Remember, uh, see, so these pipes, they're one based, but since we are, let's do this n here, right? So since n wells, they're all zero based, that's why I'm converting this one based house to zero based. Okay, and then edges, right? To sort it. Okay, again, right? So here we're only we just took care of the pipes, but we haven't added the edges for the wells, right? For that, we are going to introduce like a dummy node, right? Which we can simply so that's why I have n minus 1, because the house is from n to 0 to n minus 1. So I'm simply using the node number n to represent the dummy well, right? So which means we're gonna build dummy edges, right, from each house to the dummy node n, right? So that's why for I in C in enumerate of wells, right, also add the edges, right, for this dummy well for each of the house. Okay, so we're gonna be have C dot I, and it's always n, right? So now we have completed the graph. Now after sorting, we can simply do the union here, right? So for C dot U and V in edges, right? Oh, and one more thing, since we are going to accumulate the cost, which means that we only accumulate the cost when the union is success, right? So that's why the union here will return like a Boolean value here. So which means if union has been executed, then we return true here. Otherwise, return false, right? So basically, we do a union. So if union of U and V is a success, then that's when we accumulate the cost. Okay, and then in the end, return the answer, right? So I think that's it. Okay, submit. Cool. So it passed, right? Because, like I said, so the time complexity for both the union and find should be a theta O of 1. Okay, so we accomplish theta O of 1 by applying this. For find, by applying this path compression, and for the union by applying this ranking, right? But I skip that ranking here, and that's why the time complexity for this one is simply just a 3 for loop here, right? And it's just like O of n, I think, right? So that's the time complexity for this, and I think that's it, right? So this one is, I think it's pretty straightforward, except for the wells, right? I mean, the only tricky part for this problem is that we have to convert these wells into a bunch of dummy edges, right? So that we can utilize this union find plus Kraska algorithm to build the minimum spinning tree, right? Cool. I think that's it for this problem. And thank you for watching this video, guys. Stay tuned. See you guys soon. Bye-bye.